Lesson 7.6 on page 283 of your big book continues with the concept of algebraic expressions that we've been working with for a couple of lessons now. Our essential question: how can you use variables and algebraic expressions to solve problems? Sometimes you're missing a number that you need in order to solve a problem. You can represent a problem like this by writing in an algebraic expression in which a variable represents an unknown number. A variable is a letter that we assign to a problem to represent a number that we don't know yet. Unlock the problem. Rafe's flight from Los Angeles to New York took 5 hours. He wants to know the average speed of the plane in miles per hour. So he wants to know how fast they were flying in order to get him there in just 5 hours. So write an expression to represent the average speed of the plane. Use a variable to represent the unknown quantity. Rafe doesn't know the speed yet, so he's going to figure it out using the information that he does have. The plane's average speed is equal to the distance traveled by the time traveled. So, so we're going to look at distance, time, and the speed would be the rate. So there is a formula, a distance formula, that helps you figure this out, which we'll prove today. All right. Use a variable to represent the unknown quantity. So we're going to let D represent the distance. Traveled. What are the units of measurement for the travel? That was miles. Because remember from the original problem, miles per hour. We also know that it took him 5 hours to get there. So that's another known. So the distance in miles over 5 hours. Okay. So at the moment, Rafe doesn't know the distance off the top of his head. However, he's going to look it up so that he can have this number also. All right, so Rafe looks up the distance between Los Angeles and New York on the internet and finds the distance is 2,460 miles. Use this distance to find the average speed of Rafe's plane, or the rate at which they were flying. So now we're going to plug in 2,460 for that D, for the distance, because now we know what it is. All right, so we have 2,460 miles flying, and he was flying in the air for 5 hours. So if we divide this by 5 over 5, we're going to find out the unit rate. So I'm going to come over here and do a little margin work to figure that out. Divided by 5. 5 does not go into 2, but it does go into 24 4 times. And it does go into 46 9 times. And it goes into 10 2 times. So the rate at which, the speed at which they were flying was 492 miles per hour. That's our unit rate. That's how fast that plane was going in the air. So the plane's average speed was 492 miles per hour. So just to give you context, a car going down the highway is going about 60 miles an hour. This is, what, 9 times that fast? Not quite. 8 times that fast? 8 times as fast as a fast-moving car. Planes go really quick. Turning the page. In the problem on the previous page, the variable represented a single value, the distance in miles between Los Angeles and New York. In other situations, a variable might represent any number in a particular set of numbers, such as a set of positive numbers. So, for example, when you go to Disneyland or Magic Mountain and you want to go on a ride, and they have that little sign that says you must be at least this tall to ride in order to ride on the ride, and they'll have this little thing and you have your kids stand up next to it, and if you're not tall enough, you don't get to go on the ride. But there's an infinite number of people of heights that can go on the ride. There isn't just one number. You don't have to be exactly this tall to go on the roller coaster or whatever the ride is. You could be any one of these numbers and still go on the ride. But if you're not at least this tall, you can't. So do you see how there's a big solution set, a big set of numbers that can go on the ride? So in some cases, there's only one value for a variable. But in some other cases, there's an infinite number. There's no end to the numbers. All right, so let's take a look at some other problems that have more than one solution. Joanna makes and sells candles online. She charges $7 per candle, and shipping is $5 per order. Okay, so each candle costs $7, but no matter how many candles you order, she only charges $5 for the shipping cost, meaning putting it in a box and driving it down to the post office and paying the postage rate to ship it. So that's a constant. This doesn't change. It's only $5 per shipment. You could buy 7 candles and it would cost $5 extra for the shipping, or you could buy 2 candles and it would cost $5 extra for the shipping. Write an expression that Joanna can use to find the total cost for any candle order. Do you see how there's an infinite number of solutions for this? Some people might order 20 candles, some might order only 1. The number of candles a customer buys will vary from order to order. So we're going to let N represent the number of candles a customer buys, where N is a whole number greater than 0. So you can't buy negative candles, right? You can't buy less than 0 candles. You also wouldn't order half of a candle, right? You'd order at least 1 whole candle. So they're going to be whole numbers and they're going to be positive. They have to be greater than 0, just to be logical. All right. So the cost per order equals the charge per candle, which was $7 from up here, times the number of candles. We don't know how many candles yet. And the plus the shipping charge, which was $5. So an expression for the total cost of a candle order is 7N plus 5. Now you could have written it 7 times N plus 5, but this is more mathematically mature. All right. So that's the expression. So now she can apply this to any order that she has to figure out the cost. In March, one of Joanna's customers placed an order for 4 candles. In May, the same customer placed an order for 6 candles. What was the total charge for both orders? So the March order is here, the May order is here. So first we write the expression 7n plus 5 and 7n plus 5. Then we're going to substitute in the number of candles ordered for n. So in March, they ordered 4 candles. In May, 6 candles. So the total cost that for this customer in March was, following the order of operations, we do multiplication before addition. 7 times 4 is 28, plus the $5 shipping charge. So the total cost was $33 for the March order. Now in May, they ordered more. 7 times 6 is 42, plus 5 more is 47. So they ordered 2 more candles, and it cost more money. So now we're going to find the charge for both orders. So now we're going to combine both orders and find out how much money this person has spent on these candles. So we'll add the charge in dollars for March to the charge in dollars for May. So that's 33 plus 47. And if you need to stack them up so that you're sure to be accurate, that's okay. Teachers love margin work to know what's going on. 1 plus 4 is 5, plus 3 more is 8. So a grand total of $80 for these 2 orders. They've spent $80 on candles. All right, let's do one more together, and then we're going to do our notes. Louisa read that the highest elevation of Mount Everest is 8,848 meters. She wants to know how much higher Mount Everest is than Mount Rainier. So this is known. We know how tall Mount Everest is. We don't know how tall Mount Rainier is, at least not yet. We don't have that information. We haven't looked it up. So we're going to write an expression to represent the difference in heights of the 2 mountains. So what does this word right here mean? What operation is going on? That would be subtraction. So, and then tell what the variable in your expression represents. Well, I'm going to say R for Mount Rainier. So R equals Mount Rainier. And then I'm going to write the expression. So I would make it 8,848 minus R. I know that Mount Everest is the tallest mountain in the world. Therefore, I put it first so that the difference would come out positive. Mount Rainier is going to be shorter, so I want to subtract the height of Mount Rainier from Mount Everest. Louisa researches the elevation of Mount Rainier and finds that it's 4,392 meters. Use your expression to find the difference now. So we have 8,848 meters minus 4,392. So, where'd that extra comma come from? And what does that equal? Well, I don't know about you, but I can't subtract horizontally. I need to set it up vertically and line up my digits carefully according to their place value. And I'm going to end up with, what is that? 6, 8, 4, take away 9. Well, I guess I should leave it directly under the problem. I was just lining it up with the answer line here. Okay, so we've got 6, and I need to regroup. 14 take away 9 is 5. 7 take away 3 is 4. 4. So, meters. So, Mount Everest is 4,456 meters taller than Mount Rainier. All right, let's take a look at our notes. Okay, so one of the first things you do is you decide what operations are in the problem, like we did with the difference of Mount Rainier and Mount Everest. Difference would imply subtraction, and here in this problem, Jeff sold the pumpkins. I should rewrite that as grew. Sold for $7 each at the farmer's market. Each implies that we're going to be multiplying. I'm going to change this to grew. All right. So the first thing we do is find out the operation. The second thing we do is identify the unknown number and give it a variable. We choose a variable that helps you remember what it represents. So I chose P for pumpkins because every time I see P, I'm going to think, okay, yeah, we're talking about pumpkins. So if he sells, for every pumpkin he sells, it costs the customer $7. That would be 7 times P, right? Or 7P. That's the more mathematically mature way to write it. And our final step is to write the expression. So let's look at another one. Okay, we'll do it this way. Okay, so first we have Ina wants to serve salad at her party. She will need 1 head of lettuce for every 6 guests who attend. So for every indicates that we're going to have division. Our variable we're going to assign is G for guests. Then we write the expression. So for every guest, 1 head of, I should say that better, sorry. 1 head of lettuce will feed 6 guests. So G divided by 6 will get us the number that we need for the heads of lettuce that she needs to buy. And the more mathematically mature way of writing G divided by 6 is this. All right, finally, reviewing, write an expression. You first determine the operation, then you write the expression, solve for the assigned values, and substitute numbers for the variable using order of operations you solve. Okay, so 13 more than the product of M and 5 because this 7.6 does go on to review this concept, and so I thought this should be in our notes. More than the product. More than and product tells us the operations. Then we write the expression 13 more than, so I put a plus 13, the product of M and 5, so that's 5M. Now solve for 1 and 6. So you write the expression 5M, plus 13. Then we substitute in 1 for M and solve. We end up with 18. We plug in 6 for M and solve. We end up with 43. Okay, good luck.